In the troubled areas of the world, instant, reliable tactical communications can mean the difference between winning or losing, between life or death for our men. The armed forces of the United States can move to troubled spots on the globe and be in operation within a matter of hours. Such operations need reliable, secure communications between land, air, and sea. A system that allows the passage of command and control messages while the communication terminals are on the move. There is no single tactical communication system in existence today that completely satisfies these diverse military needs. This is the story of the military's first steps toward satisfying their most critical needs for global communications. In early 1965, the Strategic Air Command reconfirmed their requirement for satellite communications that would provide real-time tactical communications for its forces from any point on the globe. Conferences sponsored by the Department of Defense with top military and scientific leaders resulted in the go-ahead for an austere program with the Air Force to demonstrate low-rate digital communications via UHF satellite for airborne forces. SAMSO, the Space and Missile Systems Organization of the Air Force Systems Command, was designated to be the program manager for the initial program phase. In cooperation with the Aerospace Corporation, SAMSO conceived the experiment and did the basic analytical work. Scientists from Aerospace and Lincoln Laboratory of the Massachusetts Institute of Technology performed early tests on the effects of radio frequency interference, weather, foliage, and other variables on radio wave propagation. Lincoln Laboratory, already engaged in space communications research under an Air Force contract, made significant concept contributions and reoriented their efforts to provide the experimental satellite that would be put into space by a Titan 3C space booster. Simultaneously with the Lincoln Lab efforts, the Aeronautical Systems Division and the Air Force Avionics Laboratory began procurement and preparations for technical performance testing of special airborne radios adapted to operate with the Lincoln Laboratory satellite. Rome Air Development Center would provide its facilities for ground station testing. The Oklahoma Air Materiel Area of the Air Force Logistics Command went to work modifying and equipping several SAC aircraft for operational feasibility testing. The time was now late 1965, and the Army and Navy, who were studying similar communications needs, were invited to join the program. They both accepted this invitation. The Satellite Communications Project Office of the Navy's Electronic Systems Command would manage the Navy experiments. The Naval Air Test Center at Patuxent River Naval Air Station, Maryland, the Naval Underwater Sound Laboratory at New London, Connecticut, and the Naval Electronics Laboratory Center at San Diego, California, began equipping communications terminals for testing in the air, at sea, and on the ground. The entire Army participation would be contributed by their Satellite Communication Agency at Fort Monmouth, New Jersey. Army engineers began work on air-transportable ground terminals capable of simultaneous voice and teletype communications. The Air Force Cambridge Research Laboratory and the Air Weather Service joined the program to provide natural environmental forecasting, evaluation, and reporting of the effects on the communication experiments. program participants worked to a tightly coordinated schedule. Each participant was procuring, modifying, and installing terminal equipment while the satellite was under construction. The airborne and ship electronic equipment was supplied through contracts with ECI, Electronic Communications Incorporated of St. Petersburg, Florida. The modified ECI equipment consisted of off-the-shelf teletype, airborne 1,000-watt transmitters, and sensitive miniaturized solid-state receivers. ECI also built special frequency diversity equipment using a modulation method which had been conceived by scientists of the Aerospace Corporation. In addition, ECI developed the circularly polarized Loop V antenna, one of many antennas which were to be tested. At the Aerospace Corporation, radiometers were being built for installation in the Satellite and Aeronautical Systems Division aircraft to measure radio frequency interference. As installation of equipment neared completion, the satellite work was in its last phases. The result? Lincoln Experimental Satellite Number 5, nicknamed LES-5. A 225-pound cylindrical package, 6 feet long and 4 feet in diameter, LES-5 would transmit the first circularly polarized UHF communication signals from space, and would have an output of about 50 watts of effective radiated power. It featured switchable bandwidth to select either 100 or 300 kilohertz by command. In June of 1967, the satellite was delivered to Cape Kennedy, Florida. It was then integrated into a multiple payload, which contained 5 other satellites. The payload was placed aboard the Titan 3C space booster. On July 1, 1967, the Titan 3C was launched from Cape Kennedy. As the solid propellant strap-on engines neared the end of their burn time, the first stage ignited. A few seconds later, the solid propellant engines were separated, and the booster climbed further into space, propelled by the first stage liquid engines. Following their burnout by the second stage liquid engine. Shortly after, the nose fairing, no longer needed in the vacuum of space, was jettisoned. Second stage burned for about 3½ minutes, then separated, leaving the restartable third stage, or trans stage, which fired for a time period long enough to inject itself and the payload into an 82 by 97 mile-high parking orbit. About an hour later, as the vehicle made its second crossing of the equator and was headed northeast, trans stage was commanded to reignite. This short application of power changed the orbit to a transfer ellipse, which transported the payload to a near synchronous orbit at an altitude of 18,000 nautical miles. At this altitude, trans-stage reignited, turning the payload into a near equatorial plane and circularizing the orbit. Upon ejection into this orbit, LES-5 was mechanically spun to 11 RPMs. Now free in space, its antennas were automatically erected to their transmitting and receiving position. LES-5, after initial performance checks, was now available for the start of its many tri-service tests. Lincoln Laboratory began the experiments with its mobile terminal, its tactical transmission system, and a unique device called a message composer. The message composer allows the operator to type a message which appears on an oscilloscope above the keyboard, verify its content, correct any mistakes, and when the message is complete, transmit it. The oscilloscope shows the message as it is being transmitted to and received from LES-5, and the time lag involved. a Navy P-3A aircraft over the Atlantic conducted the first military tactical satellite communication between the submarine USS Sea Leopard on the Virginia coast, the carrier USS Iwo Jima off the California coast, shore stations located at Point Loma near San Diego, California, Point Lookout in Maryland, and a fixed communications van at Fisher's Island, Connecticut. The Aeronautical Systems Division's airborne terminals made the first air-to-air communications. Subsequently, a SAC KC-135 made air-to-air teletype contact with B-52s, tankers, Aeronautical Systems Division aircraft, and a Navy aircraft. The Army conducted voice and teletype testing at Fort Monmouth, New Jersey, between its jeeps, 3/4-ton truck terminals, and a transportable communications van. Strike Command initiated voice and teletype testing between their mobile terminals near Tampa, Florida, and a fixed terminal at St. Petersburg, Florida. The first joint service test was a roll call originating from the Rome Air Development Center ground station to all participating terminals, and was completely successful. All this forementioned testing was accomplished in the first 36 hours of satellite life. Since then, SAC test aircraft have been conducting joint service roll calls on a routine schedule. The Aeronautical Systems Division has done testing over locations around the world, including Southeast Asia. The Navy has continued testing with its submarine, ships, ground stations, and plane from sea level to 22,000 feet altitude. The Army performed extensive successful testing in the jungles of Panama to determine the effects of extremely heavy foliage and other tropical conditions on communications. Some examples of the most significant global coverage include teletype communications between Vietnam and San Diego, the Arctic and Rome, New York, Hawaii and a location near Ireland, and from the Middle East to Florida. In addition, teletype and multiple access voice communications were tested between selected NATO participants. The program objectives were achieved. All experimental equipment performed successfully. The operational and technical feasibility of using a UHF repeater satellite for tactical communications was demonstrated for links involving airplanes, ships, submarines, and vehicle-mounted terminals. As intended, the LES-5 satellite was an extremely successful test tool. It confirmed several features which an operational tactical communications satellite should embody. A synchronous orbit with position keeping is preferred because of the availability and operational problems which accompany drifting satellites. Recommended features for follow-on development are higher power for greater margins and more users, high-gain circularly polarized antennas to simplify terminal antenna designs, and increased repeater bandwidth to give more accesses with jamming and interference resistance. The airborne and ship terminal equipment tended to be larger, heavier, and more difficult to operate than radios recommended for operational use. This equipment was procured and adapted for these tests and was not designed specifically for this tactical application. The Army terminals were built and proved suitable for tactical use. The fact that UHF antenna performance makes the UHF band most attractive for airborne tactical communications via satellite was proven. Several antennas were evaluated for each type of tactical terminal. On the airplane, testing included a linearly polarized blade antenna and 3 circularly polarized antennas, the ECI Loop V, the Dorn Margolin, and the Lincoln Lab cross slot, which offers a flush profile for operational use. On board ship, the stacked dipole, the helix, and the truncated conical spiral were each tested. The submarine used two antennas, a vertically polarized dipole and a steerable array mounted on a telescoping mast. The Army vehicles used high-gain helix and Yagi designs. The antenna test results showed areas for improvement and development in patterns and profiles for operational antennas. The modulation techniques successfully tested included the ECI 60 words per minute teletype with frequency diversity which provides fading resistance, the Lincoln Lab spread spectrum tactical transmission system which offers multiple access and resistance to fading and interference, and from ground terminals, conventional FM analog voice and 100 words per minute teletype, facsimile, and data signals. The input-output devices tested by the military were conventional commercial gear. The Lincoln Lab Message Composer was a significant improvement, but continued development for these devices is needed. National Cash Register, under an Air Force contract, is providing the next step in such message composers. The multipath fading encountered by earlier satellite and aircraft tests over water, snow, and ice was successfully overcome by the use of the Lincoln Lab and ECI modulation techniques in combination with the circularly polarized antenna on the satellite. Good links were maintained down to 0-degree look angles, which means the satellite can be used anywhere above the horizon. This signal strength plot of actual test data shows uncorrelated fading occurring on 6 channels. The information is transmitted simultaneously on each channel, but fading occurs at different times, so no errors are encountered. Correlated fading and errors occurred only when the satellite was on the horizon. Some minor natural environmental effects from weather and storms were observed. The scintillation fading caused by the ionospheric activity, weather blockage, and interference indicated no significant communication degradation. The propagation through heavy foliage showed noticeable attenuation, sometimes as high as 8 decibels, but communication was possible through it. If this experiment had used microwave frequency under similar conditions, communication would most likely have been impossible. Radio frequency interference occasionally produced minor problems. For the satellite, only very strong signals interfered. By frequency selection and system design, these interference problems can be avoided. For tactical terminals, the most serious interference was generated from onboard ship radar and airborne high-frequency transmissions. The selection of frequencies, filtering, and operating procedures successfully countered these problems. The heaviest utilization of the military UHF spectrum was found over Southeast Asia. However, the use of spread spectrum modulation techniques and/or frequency discipline appears sufficient to allow operation in that environment. In summary, LES-5 was successful in passing varied kinds of communications traffic, 60 and 100 words per minute teletype, voice and vocoded voice, facsimile, and data information. LES-5, now having done its job for the military, will be made available for experiments by universities and industry. This initial program phase has proved that tactical communications via UHF satellite are feasible and shows the direction to take for future tactical communication satellites. Work on the subsequent program phases is already advancing. LES-6, the 375-pound follow-on satellite to LES-5, is scheduled for launch by a Titan 3C into synchronous orbit. It will have additional solar cell panels, electronically despun antennas, increased output power, and will feature a position-keeping ability. The Coordinated Joint Service Testing with LES-6 will be managed by the Electronic Systems Division of the Air Force Systems Command. Beyond LES-6 is the huge Tactical Communications Satellite number 1, being produced by the Hughes Aircraft Company. The largest communications satellite yet built, this 28-foot tall spacecraft will weigh 1,600 pounds, provide greatly increased power, and mechanically despun antennas. It will have the capability to repeat communications on either UHF or microwave frequencies, and the ability to receive a message in one band and transmit it in the other band. Like the LES-6, the Hughes satellite will be position kept and will be launched using a Titan 3C space booster. These experimental tactical communications satellites may, in the near future, lead to an operational tactical satellite system which will serve the needs of tactical forces throughout the world for positive command and control. Our military commanders soon may no longer be bound by distance in directing tactical operations.